Hi, this video is a part of Machine Learning from Scratch playlist. In this playlist, I explain different machine learning algorithms implemented from scratch using Python. You can download the relevant Python files from the link given in the description of each video. Note that I do not code along, rather I make use of pen for explaining the tricky parts of code so that you people can read the notebooks and understand them yourself, and of course re-implement them yourself. Now I'm expecting my audience to be well versed with machine learning general understanding, and they just need little hints for implementation these algorithms from scratch. In this video, I'll explain development of advanced nearest neighbors algorithm based on fuzzy clustering. We will first understand the implementation of fuzzy C-means clustering and fuzzy Gustafson-Kissel clustering algorithm, which is also known as GK clustering algorithm. So fuzzy C-means and fuzzy GK clustering algorithm, we will understand the difference between them. There is a very minor difference of it. The difference is basically in the calculation of distance. We'll look into it, and then using these clustering algorithms, we will work on applying these clustering algorithms for nearest neighbors regression. So let's jump to the notebook, let's jump to the whiteboard and then notebook to understand this idea further. Let's begin our understanding by looking at the difference between k-means and fuzzy clustering. So in k-means, we have hard cluster assignments where we assign a sample to one of the cluster. For example, sample number 1 is assigned to cluster number 2, sample number 2 is assigned to cluster number 1, sample number 3 is assigned to cluster number 1, sample number 4 is assigned to cluster number 2. But in fuzzy clustering, the idea is that there is kind of uncertainty in association of a sample to a cluster. So what we say is sample number 1 is assigned to cluster number 2 with membership of 0.8. It means it has a very great association with cluster 2, but there is in association with cluster 1 also with a membership of 0.2. So there is an uncertainty of 20%. We could, if intuitively I want to, if I may say intuitively. The same goes for sample number 2. So it is more associated with cluster 1 with membership of 0.9, but there is also 0.1 membership for cluster number 2. So there is less uncertainty in sample number 2. And even lesser uncertainty in sample number 4, where there is only 0.05 membership for cluster number 1 and 0.95 membership value for cluster number 2. So in a way, we are incorporating the uncertainty in the form of memberships, and this is what we call fuzziness. The more fuzziness is, so the more kind of uncertainty we can incorporate. So this is kind of a hyperparameter. Now, how do basically clustering works? Any clustering work by initializing the memberships, initializing the class centers basically. But in fuzzy clustering, we initialize the memberships. So in k-means, we can initialize this hard assignments. So this is like initialization step. In each clustering algorithm, the initialization step is there. Then we update the class center. Then we calculate the distance of samples from that class centers. Then we update the assignments or the membership values in case of fuzzy clustering. Now, this whole thing is really simple, and I hope you know about it. But in case of fuzzy clustering, we are dealing with two different kind of algorithms. One is fuzzy C-means and another one is fuzzy Gustafson-Kissel algorithm. In fuzzy C-means, what we are saying is that we use regular Euclidean distance from what you call this class center and the samples. But in fuzzy Gustafson-Kissel algorithm, in GK algorithm, what we say is that no, instead of simple Euclidean distance, use Mahalanobis distance, and even use the fuzzy form of Mahalanobis distance. So this is because we are dealing with membership values, so we also have to incorporate that in finding out this covariance matrix. So Mahalanobis distance make use of covariance matrix, and what is the benefit of that? The benefit is that it captures the spatial continuity in space. So this is like finding out the hidden structure and making use of that hidden structure or hidden pattern inside the data. So this is usually better whenever there is kind of a correlation between input feature space, or there is some kind of a pattern. So I hope so you know about this spatial continuity kind of a concept and the importance of this Mahalanobis distance. If you know about it, so you will understand the importance of fuzzy GK algorithm. But fuzzy C-means is also very well known, and it's used oftenly. Now let me show this whole thing in coding that you will understand it more clearly. Let me just jump to the coding part where we initialize this class. Then in fitting function, in the fit function, we do these four things. First of all, we initialize these memberships. After initializing, we update the class centers based on the data and membership values. Then we calculate the distance, and after calculating the distance, we update these memberships. So initializing the memberships, updating the centers, class centers, calculating the distance, updating again the membership, and then breaking whenever the threshold is value is achieved. The change is minimum. Okay, so what we do is in the initializing membership function, we just randomly initialize the membership for each of the class and cluster, given a different number of clusters. Suppose if there are three clusters, so we will be having total number of samples, comma clusters, metrics. Now these lines are just to make the values equal to 1. So this is like normalization, so that the clusters sum to 1. Okay. Why? Because probabilities always add to 1, and uncertainty, incorporating uncertainty, is actually finding out the probability of a sample association with the class center. Now once we have initialized the membership, then what we do is we update the class centers. In fuzzy clustering, we update if we are dealing with the soft clusters, not hard clusters, in a way, if we are dealing with membership values, so we update class centers using this formula. This might seem little difficult. Let me show you the formula. This is the formula for updating the class center in case of fuzzy clustering algorithm. So what is this? So if you look at it, these are the membership values. This m is a fuzziness parameter. This is input data, and this is summation of all of the membership values, fuzzy membership values. So if we look at it here in the coding part, so this is actually multiplying the fuzziness value with the membership, and this is just the numerator part, and this is the denominator part. So we update the class centers. Once we updated the class centers, then we calculate the fuzzy covariance matrix. Then we calculate the distance basically. And if we are using simple C-means algorithm, then we do not need to worry about this part and even this covariance part. We just have to calculate the Euclidean distance or any other Manhattan distance or any other distance between the class centers and the data points. So this line is enough for calculating the distance. But if we are using the GK algorithm, in that case, what we will do is we will calculate the fuzzy covariance matrix. What is the formula for that? Let me show you the formula for that. But you can search it out and explain it and explore it yourself. So this is basically, if we look at it, this is basically finding out, setting the stage for finding out the fuzzy covariance matrix. So the function is actually calculating this whole thing. And inside that we have this S star. S star is calculated by multiplying this fuzzy membership with this difference of class centers and samples. Let me show you in code how I have encoded it. So this is again that fuzzy membership where I multiply the membership with the fuzziness index. Then what we do is we calculate the difference. This difference is x minus class centers. Then the left value is multiplying this whole thing together. This is what I'm doing. This fuzzy membership is this is a dot product of difference with itself. So this is like a x minus class grade centers multiplied by x minus class grade centers transpose. So then we multiply it with this fuzzy membership value and we divide it by fuzzy membership values. So we get the value of S star. Then we take the determinant of this S star and we take the power with respect to -1 by p, where p is the number of dimensions, total number of features, and then again we multiply it with the S star. So we get the fuzzy covariance matrix. This is what we are doing. Here I am taking the determinant part, and then after taking the determinant part, I am multiplying with this -1 by dimension part, and then multiplying again with the S star part. So left is actually S star. So once we calculate this part, then we calculate the fuzzy covariance matrix by simply multiplying this difference value with the fuzzy covariance inverse. We take the inverse of this SI that we just calculated, here. So if we look at it, this is what we are doing. So we are taking the inverse of whatever I have calculated after taking the determinant and multiplying it with the dimension and S star part. I take the inverse of it, and after taking the inverse, I just append it and store it in the list. So we have the fuzzy covariance inverse matrix up till now using this function. Once we have that, then what we do is we calculate the Mahalanobis distance, and Mahalanobis distance is actually calculated using this whole part where I multiply this S inverse that I have just calculated by multiplying with this difference transpose and this difference. So I'm calculating this difference and the covariance inverse, and this is how I get the Mahalanobis distance. I think so. If you understand the formula, then you can implement it even yourself. It is really simple. I have broken it down into two classes, one where I calculate the fuzzy covariance and another one where I calculate the Mahalanobis distance using that fuzzy covariance matrix. Why I have done it? Because it's easier to understand separately this fuzzy covariance matrix, and it can be used even elsewhere. So if you have this logic for fuzzy covariance matrix, then it's better, I think so. Okay, once we have calculated the distance, we update the membership, and you can find out the updating part anywhere in internet, the formula where how can you update the memberships for fuzzy clustering algorithm. So this is just making use of the distance. Given the distance matrix, we update the class centers and membership values. So once membership values are updated, then again we update the class center, then again we calculate the fuzzy covariance matrix, and then this thing repeats again and again. So this is how fuzzy clustering works. If you are not making use of GK clustering algorithm, then the whole thing is extremely simple. But if you are making use of GK clustering algorithm, which is robust in capturing the spatial continuity and spatial patterns, then if you understand the formula, then again it's easy. It's not a difficult part. I hope so. It makes sense now. The clustering part makes sense now. Okay, once we understand this fuzzy clustering, let's come to the nearest neighbors part where we make use of this fuzzy clustering. So for each test point, what we do is we look at the surrounding samples in search neighborhood, and we assign to each of the surrounding sample in that search neighborhood a membership value based on its distance from the test point. And that distance could be Euclidean, but we here use fuzzy Mahalanobis distance to make use of that spatial pattern and spatial structure, as I explained. So we will calculate this fuzzy Mahalanobis distance between this test point and the surrounding samples, and then based on that fuzzy Mahalanobis distance, we will give membership to each of the surrounding sample. So this is what we call antecedent membership of each of the surrounding sample to test point. Then before I explain this point, let's come to the second point, a third point, where we find out the effect of each surrounding sample by multiplying this antecedent membership with its own membership to class centers. So each surrounding sample has some membership to different class centers, different clusters. These are same thing, like different clusters. So whatever the antecedent membership is of a specific surrounding sample to the test point, we multiply it with the membership of that surrounding sample to cluster I. We do it for all the cluster. So in this manner, we find out the consequent memberships for all the surrounding samples, and to all the class centers, to all the clusters. So suppose we have this test point, and this is another training point which is in the search neighborhood. So first of all, we will calculate the antecedent membership. Then this training sample will be having some membership to class 1 and some to cluster 2, some to cluster 3. Suppose we are using 3 clusters. Then using this antecedent membership, when multiplied with this class 1 membership of this training sample, we get the consequent membership for cluster 1. Then when this antecedent membership is multiplied with this class 2, then we get consequent membership for class 2. In the same way for class 3. So in a way, what we find out is antecedent memberships and consequent membership. So the effect of each neighboring sample is actually now encoded in this consequent membership. I hope so you understand this and the intuition behind how it is capturing this effect. I am not here explaining the details and mathematics because this is majorly to encode it and to make you understand bits of the encoding part. So let me just show you what they call this formula. So this formula is for antecedent membership, where this distance is coming from this formula. This is showing the fuzzy Mahalanobis distance, and this sigma is showing is kind of encoding the information of search neighborhood. So greater the sigma, lower will be the search neighborhood. Lower the sigma, greater will be the search neighborhood. Okay, let me show you this antecedent membership part encoding. So we initialize this class, and in this class we are inheriting it from clustering class that we previously discussed. So we apply the clustering algorithm to find out the optimum membership values and optimum class centers for training points. Once we apply the clustering, then we calculate the fuzzy covariance matrix between test points and the training points. That is what we have done here. that is a membership that is a function that we have already discussed in the covariance part. So then what we do is we find out the antecedent membership making use of this fuzzy covariance matrix, and using this fuzzy covariance matrix we calculate this antecedent membership values. Just let me show you. So this is the sigma is used for this what you call a search neighborhood kind of a thing. This is finding the exponential and minus distance to power 2. I hope so till now we are clear. So leave this what you call function for now. Let me show you the consequent membership function, but before that let me go in sequence. It will be much easier for you. So we have till now looked at the antecedent membership, and I have already told you the use of antecedent membership in calculation of this consequent membership values. Now another thing that we do is fit the linear regression model to each of the cluster membership values. Why we do it? Because for test point we want to predict the cluster membership values using the fitted linear regression model. We could also use nonlinear model, but and there is a research going on in that, and this is a really great idea to use kind of a random forest or any nonlinear model. You could play with it, but this is done to predict for each test point the cluster membership for each of the cluster. So once we have that, so finally what we do is we finally do the prediction for class center I using the consequent membership of surrounding sample to the class center I and the predicted membership after applying this linear regression for test point to class center I. So this is simple multiplication. Let me show you this whole thing in coding. So after calculating, after clustering, we calculate the fuzzy covariance matrix. After calculating that, we calculate the antecedent memberships. After calculating the antecedent membership, we fit the linear regression model, and we fit it using this formula. And this is a formula for multiple linear regression. This is a closed form solution. If you look at this part here, so this is the formula for multiple linear regression in closed form. You can find it out anywhere in internet. It's very well known. Now, once we have fitted the linear regression, then we've given the test data point, we predict the class center memberships, cluster memberships for each of the test point. This is the formula for that. So once we have predicted that, then we calculate the consequent memberships. Consequent memberships make use of antecedent memberships and the sample's own membership to the class centers, as I explained. This is encoded in alpha. Then we normalize it basically. So somehow this is like calculating that consequent membership. Once we have that consequent membership, then our job is done. Then all of the functions below are just combining the above pieces together. So in this function, I'm just calling consequent membership, and in this fit final function, I'm calling the above fit init function, and inside fit regression, I'm calling this fit final function. And finally, when I call this fit final function, so I have all the things: the final predicted value after applying the linear regression model, the final consequent membership, and the neighboring samples. So using the final predicted value and the final consequent membership, we predict the final value. Now this is in the else block. If block contains the code for localized regression, where we divide the space into subspace, but this is not important. This is just a minor detail, a minor tweak in the algorithm, but main logic remains the same. So the whole process is really easy and really easy to follow and understand once we know the concept of consequent membership and antecedent membership and linear regression. So these are the 4 steps where we find out the antecedent membership, we fit the linear regression model, we find the consequent memberships, and then we do the final prediction using this consequent membership and this linear regression model prediction. I think so it's easy enough. In this way, we do the nearest neighbor regression, making use of those fuzzy clusters.